Okay, Assalamualaikum warahmatullahi wabarakatuh and good morning to you all. So we meet again today, Monday. So please make sure that you have got your quiz number 2. So I'll give you the time for you to download the quiz. And then in 1 minute or so, I'm going to explain how you will answer the quiz. And don't forget also to fill in your attendance. All right, so hopefully everybody, you have downloaded your quiz and also you have done with your attendance. All right, let me explain the quiz. So the way you do it is the same as what you have done last week on your quiz number 1. So this is quiz number 2. And as I promised, this is going to be the quiz on what I explained last week regarding still the same finite element modeling. So let me do the presentation of the quiz. Okay, do you see what I have here on the screen? So this is Microsoft Word version of the quiz, quiz number 2. Could you respond to that, please?
Yes.
All right. So this is your quiz number 2. As usual, you do it in the same as what we have done last week. So we have this structure, which if you look at this, basically this is in plane problem. That means you are going to use a membrane element or in plane element. And your job here is to do as instruction as given here from number 1 to number 4. So we have loads over here, another load over here, and then you have supports in the forms of two pin joint support at the top and at the bottom of this left edge of the structure. So the shape of the structure is triangle, all right? And the way you do your finite element modeling is up to you. So every student, they might have different models. So it's up to you, basically. Number one, um, you have to do meshing, all right? You have to do meshing using triangle. You have to do meshing using triangular elements. Remember again, remember what I have explained to you regarding the procedure and the rule to do meshing, where you put the nodes, etc. Okay, don't forget when you have finite element model, you need to have element number and node number, both of them. I want to see the node number and I want to see the element number. Without node number, without you put node number, you cannot answer question 3 and 4, and actually also question 2. So please make sure you have not only element, but also node number. And in your finite element model, I want also to see you put, don't forget, the support and the load. Okay, remember what we call as finite element model. So that's number one. Number two is based on your finite element model, then you need to answer the size. Is it 1 by 1, 2 by 2, or 10 by 10, 20 by 20? The size of K before and after introduction of boundary condition. For example, probably before boundary condition, it is 50 by 50. After boundary condition, becoming 40 by 40. Okay, and that depends on your supports. And the next is going to be based on your node numbering. You have to answer what you know. If you can put a number, you can put a number. If otherwise, then state what you understand of, well, you have to answer question number 3 and number 4. Number 3 is on displacement. Number 4 is on the forces. Remember the answer based on your finite element model node numbering. All right. So that's my explanation. Don't forget to write down your name and student number and also save it in PDF. Okay, save it in PDF and give the file name as your name. The file name as your name. All right, so you can start now. Okay, you have to submit to my email, the same email as you submit last week, not later than 8:30. So I have given you 10 minutes to do it for everything. Okay, so you can start now.
Yeah.
Okay, so we have finished our quiz session. I'm not going to accept anymore any submission from you. All right, so let's see how we will answer the quiz. So for that, I'm going to go to presentation mode. Okay, so so now I'm going to show you the way we answer. The way I answer might not be the same to the way you answer. Okay, so because that depends on your finite element model. So now for that, I'm going to go to this is Microsoft Paint. Okay, can you respond to me? Can you see what we have here? We have a triangular structure.
Yes, bro.
All right, so that is a structure. So what we need to do first is we need to build the finite element model based on this structure. And number one that you have to do is you have to specify the location of the node. So that's number one. We discussed this last week, I think last week or before. Is it the third week, I suppose, today? Okay, anyway. So number one, when when you see a force, applied force, then you must have a node over there. Okay, so that's what I'm going to do now. I'm going to have the node over here and over here. The reason is because we have applied force over there. So that's the way we, the proper way, if I may say so, the standard way of having node location, which is going to be where you see an applied force, then of course you must have the node over there. Number two, the procedure is going to be, if you see we have a support, then you must have the node over there. So you must have the node over here and over here. Okay, so over there, can I draw it here? So you must have it over here and also over there. Fine. Next thing here is that you need to have the node. You need to have the node if we are at the corner. Okay, if you look at this shape, the corner is going to be over there, and over there. So you have three corners. But of course, you already have the node over there because the corner somehow is also where you have this force, 500 newtons, and the top left corner is where you have the support, and the bottom corner is also where you have your support. So meaning that you don't need to put a node there because it is having a node already. What else? Okay, so more or less based on our general rules of where you must put a node, then you have identified all the nodes that you need to have. And then you need to put a numbering on that node. So this is going to be number 1. This is number 2. This is number 3. And this is number 4. Okay. Do I need to put any more nodes here? Well, that depends. Depends on whether the mapping of your triangle is going to need nodes or not. But if you look at what we have here, okay, so what I'm going to do next is I'm going to specify the element, and the element is of course triangle. So I will take a line, I will draw a line like that. So now what we have here is we have 2 elements, okay, and 4 nodes. Is it sufficient? Yes, it is sufficient, because for every triangle you have a node. Okay, for every triangle you have a node. So for the first triangle here, then you have node 1, 2, and 4. And for the second triangle, you have node 2, 3, and 4. What does it mean? It means that you have specified a triangle complete with nodes at the corner. That means, yes, that is going to be our finite element model is sufficient. And this is what we call as minimum model, minimum size of model. That means for this structure, the minimum number of nodes that you need is going to be 4, and the minimum number of elements that you are going to need is going to be 2. So if you answer like this, then this is correct answer. What about if, let's say, your answer is, let's say, you see that, okay, the structure is a triangle, all right, and then I put the node, for example, like this, but somehow you decide that I want to have only one element. Okay, you want to have only one element, element number 1, one element, and you feel it is okay because it is mapped properly. The structure is a triangle, and then the shape of the structure is a triangle, and then okay, then that means I have one triangular element only, and that is sufficient. Then you are wrong. The answer is wrong. The reason is because if you decide to have one triangle, you have extra node over here. You cannot have, based on what you have learned here, a triangle with node at the corner and one hanging node over here. You cannot. So the meaning that this is a wrong finite element model. The way you can do, for example, is like this. You might add one more node over here, for example, node number 5. Okay, and then you can draw a line like that. Then that's fine, because now you have element number 1, element number 2, element number 3. Then you are okay. All right. So as I mentioned before, the way you do your finite element modeling is again based on what you have in terms of your finite element modeling. So depends on your node numbering, depends on your element numbering, etc. Okay. So now, for the sake of let's change the numbering. For example, you have this number 3, and then this is number 4, sorry, and this is number 5. Right. So let's say we decide that this is our finite element model, and then let's look at the question number 3 and number 2. Okay, the size of your structural stiffness matrix before and after you introduce the boundary condition. Okay, so the size of your structure stiffness matrix K, that's going to be 10 by 10. The reason is because in this model, you have 5 nodes, 1, 2, 3, 4, 5. And for every node, you got 2 degrees of freedom, and that means it is becoming 10 by 10. What about after I introduce the boundary condition? So you see here, we have 2 supports, this support and that support. Okay? And you understand that for every support, because it's pin joint, it will have 2 displacement in X and Y. So at node number 1, you have D1X, D1Y. At node number 5, you have D5X, D5Y. But of course, because we have pin joint, D1X, D1Y, D5X, D5Y, they are all 0. So that means what? That means for displacements, they are 0 displacement because it is pin joint. That means the K after you introduce the boundary condition is going to be 6 by 6. All right, so that's the way you answer question number 2. Before boundary condition 10 by 10, after boundary condition 6 by 6. Next is, what is the value of D1Y and D4Y? So let's look at D1Y, D4Y. So D1Y is the support. D4Y, as we have over here, is that node. Okay. So now if you look at this here, D1Y, that's the equation, D1Y is displacement at node number 1 at Y direction. You remember the question of last week? You understand D1Y, then you can specify that D1Y is 0. Okay? The reason is because in node number 1, in Y direction, it cannot move. The reason is because it is support. What about the next question? D for Y. That's D for Y, the next question. So D for Y is going to be over here. At node number 4, okay, in Y direction, then D4Y. How are you going to answer that? You simply say that D4Y is unknown. D4Y might not be 0 because it can move, but you do not know the value of it because it is variable. Okay? How you answer that? In writing, up to you. But I understand from the way you write, whether you understand, whether you can answer or not. So next question, the final question. F1Y and F4Y. F1Y is again at that support. F1Y is reaction force. So it is not 0. It might not be 0, F1Y, because it is support. That means it will have reaction in Y direction. What is the value? We do not know. We do not know. The force value that you know is at node number 2, 3, and 4. Okay? Applied force 2, 3, 4, you know. But as a reaction at node number 1, you do not know. And final question here is going to be, let me see again, F for Y. which is that node. F4y is equal to 0. The reason is, well, there is a force over there, but it is 0. If you look at node number 3 here, for example, F3x is 500, for example, right? So from here, you know, I hope from here, from this quiz, you learn how to interpret your own finite element model. Okay, so as I promised last week, I'm going to check your understanding on whether you understand how to do finite element modeling and whether you can read your own finite element model, because it is important that you understand, you can specify all these parameters, because if you do not know how to do it, then of course you cannot solve your finite element problem. All right. So that conclude the quiz of today. I try to do another quiz next week. So as you see here, the quiz is basically for me to check whether you understand or not. So as you see here, actually the quiz is very easy. You can finish in less than 5 minutes actually. Okay, is there any question regarding to your quiz? Please ask me now. Question, please.
Prof. So
Yep.
the where we put our note does not matter, right? I mean the number for each note. So it does not matter if we put the 500 Newton is not 1, the pin is not 4.
Very true. Very true. Because the way I draw my finite element model is not necessarily the same as how you do it. That's number one. And then even though the node location is the same, the element positioning is the same, but the numbering can be very different. And actually it's like this. It's not necessary that you put your numbering as node 1, 2, 3, 4. You can put your node numbering as node 100, 101, 102, or you can put it as node number 10, node number 20, but that's going to be weird. That's going to be unusual. So normally the way we do it, we start with a low number 1, of course, and then you have number 2, number 3, etc., up to the, well, to the maximum number of nodes that you can have. But again, the answer to your question, the positioning of the node, yes, it is important based on our rule. What is the rule? When you have the force, okay, when you have the load, you have the node. When you have the support, you have the node. When you are at the border, you have the node. When you are at the corner, you have the node. When the cross-section change, you have the node. When the material change at the intersection, you have the node. That's what we discussed. I can't remember, is it last week or 2 weeks ago? But that's the way we do it. But the numbering up to you. So meaning now, this numbering is my own numbering. So meaning now, if let's say this is number 4, okay, let's say this is number 4, right. This is number 4. Let me do it properly. Okay, that's number 4. And that's number 2. Then of course, F4Y is not 0. Look at this here. This is not number 4. F4Y is not 0. F4Y is going to become not 0, but it is going to be minus 1,000 Newton. Okay. And then of course, your node number one might not be here. Your node number one might be somewhere else. So meaning that, yeah, the way you answer is going to be based on your modeling. That is the reason why for question number 3 and question number 4, look at the question. I have underlined based on your FE model. Based on your FE model. Because later on, when you do tests, for example, then what I give you is a structure. I don't give you a finite element model. I will give you a structure, and then you do your finite model of your own, and then you answer your own that question based on your own finite element model. And then, of course, that means the numbering is going to be your own numbering. Okay, next question. Any other question? Okay, so now you have done your quiz. You have 2 quizzes done. For the second quiz, not every student can submit their answer. Probably they do not know how to answer. But yeah, this is the way I measure your understanding from this simple quiz. Okay, and I force you to come early in the morning. So if you wake up late, then of course you cannot join your quiz. So to do your quiz properly, of course you should be on time. All right. Okay, so the quiz number 3 is going to be next Monday. Okay, so that's the way I do it, by doing this, and hopefully you understand finite. All right, so now let's move on to our course today. So I'm going to erase. No, I'm not going to erase this. I'm going to push this down. All right. Fine. Yeah, I hope you enjoy your quiz. Very easy, right? Actually, as long as you understand what I explained to you, then the quiz should be no problem. Okay. So what we are going to do today is we will begin to do analysis. We will begin to do calculation. And I'm going to start with the simplest element that you could do. Hold on, it is 8:58 already. Okay, so I think I will give you 10 minutes break. And not only you, I need that 10 minutes break. So we'll start at 10 past 9, okay? 10 minutes past 9 o'clock, 9:10. So we'll come back at 9:10. All right. So I think that's it. Yeah, we'll meet again. So it's not a goodbye. So we'll meet again at 9:10. See you then. The way we do the modeling. Right?
Can you repeat
Yes.
session?
Yes. Yep. Can I sorry, what's the problem?
Can you record this class session?
Can I yeah, Nurhaniza, what's your question? I cannot hear clearly. It's a bit broken, the connection, probably.
Can you record this class session?
Ah, all right. Okay, yes. Sorry. I forgot. Let me record it. Thank you for reminding how to do recording. Okay. Thank you for reminding me what I'm going to say. Okay, so you have done your quiz, so you have done your lab. Then you understand what finite element modeling is. You understand the concept of element. You know what node is, okay, and you have tried to do your finite element modeling, and you also begin to interpret your model. That means it is going to be should be not that difficult for you to understand. In fact, should be easy for you to understand what we are going to discuss. So for analysis, for calculations, the way I explain to you is by beginning to introduce you with the simplest, the most simple, the simplest type of element, that is spring. Spring and bar. Okay, spring and bar. You are going to see what spring and bar is. But I think from the name, spring is very obvious. We are talking about spring. And bar, what is bar? We are going to talk about it later. So for that, then I'm going to share to do a presentation mode again. Excuse me. Okay, so on my screen here, I have a PDF slide, and the title is Spring and Bar. Can you see this?
Yes.
Fine. Okay, so what we will have here is what we are going to discuss here is the mathematical side of finite element analysis. As I think I believe I explained to you before that every element is actually an equation. Okay, so every element that you set, every element that you create, that you have at your model, every element represent an equation, and that equation is F equal to KD. Okay, F equal to KD. So every element is equation. And normally what we want to define first in terms of analysis, we want to calculate the value of K. We want to calculate the value of K. And from what we have discussed, you understand that the element equation is the same for every element type. F equal to KD. But of course, you also realize that the content of F for every element, for different type of element, they are not the same. They are not the same. Depends on the type of element, the behavior, the degrees of freedom, that kind of thing, right? And of course, the K is the size not the same. When we talk about triangle membrane, then the size is going to be 6 by 6. And I think I've also shown you how the element looks like. So now what we are going to learn is how you want to calculate the K. And of course, you need to know how the K is going to look like for every element. So what we are going to learn today is in a simple way, we are going to derive the K, or the element stiffness matrix, or actually what we want to derive is the element equation itself. So we are going to derive our own element equation. And for this, I'm going to, for illustration, we are going to look at spring element and bar element. And the method that we are going to use is what we call a stiffness method, or Normally I call it force displacement method. It's only name. Okay. Right. So that's what we try to do. Spring and bar. We are going to start with spring. So what you see over there is spring. Okay. What you see over there is spring. On the right here, you have a short spring. On the right, you got a longer spring. And you have learned from your SPM that when we talk about spring, then we talk about spring stiffness, K, spring stiffness K. I Okay, I hope you see that K over there. So when you buy a spring from, I don't know from where, from material shop, from DIY probably, um, from Ace Hardware, for example, then I suppose you want to specify, I want to buy a spring of certain dimension with the spring stiffness as, well, probably 1000 Newton per millimeter, probably, okay? So meaning that is the way we talk about spring. You need to know your spring stiffness. So probably from these two picture of spring, the spring at the left here most probably is going to be higher than the spring on the right here on its K value, the spring stiffness. Probably just looking at the shape. And of course, the spring can be in different size, can be with different properties. As you look at what we have over here, then you have a different type of spring. Now you imagine that you can connect your spring one to another, and then you can apply the load. Okay, so then you have your spring structures. So what you have here is, for example, is you have three springs. You have three springs, and if you read the K here, then that means 200 each, 200,000 Newton per meter. Then you have the same spring. So the same spring, type of spring, then you connect one to another, and you have to, then you have the spring in series, for example. This is what we call as series connection of spring. And how you connect is up to you. There are many ways to do it. And then at the edge, you got a force 20 kilonewton to the right. And on the somewhere over here, which is the connection, the border between the spring on the left and then the spring on the middle, you got a force to the left direction, 5 kilonewton, not kilometer, yeah? Kilonewton to the left. So that is the problem which you need to understand. That means you know where the loads are being applied, and you also know where will be the forces, and also how the elements are connected, and also we know that it is being supported there. So the difference between the top and the bottom here is that the top, the support is at the left. At the bottom here, the support is at the left and right ends. So now we have different boundary condition. And the force is being applied at the connection between the spring at the middle and the spring on the right. So you see here that this is our spring. And of course, you can have your spring configured such as the one at the left here, okay, and with different spring stiffness, 40, 80, 50, and you got a force over here and over there. All right, just to give you the idea how your spring structure is going to look like. And also over here, we have bar structures. Bar structure. So if you look at the structure on the right here, then I hope you agree with me that you have a kind of three component. Um, one here, you know, the length, the component at the middle, you got the length as well, and also the element at the end. And you can observe that the cross section of the element at the end is not the same to the others. I'm not sure whether the element 1 and 2 they are having the same, if they are the same cross section, not sure. And then there's another example here of bar structure. Um, we have two different segments on the left and on the right, and the support is at the middle to the right, and the support is at the left and on the right. Over here on the right here, and the support is at the top, and you have the forces at each of the interface. And then this is another type of another structure, bar structure. And then you have the force on the right edge, and the cross section, they are not the same. Okay, and then you know the length of it. So this is basically bar structure. I hope if you look at, let's say from this figure here, then you see that the axis of every segment is the same. The axis of every segment is the same. So the axis of every segment is, you see the red color? All right, that red color is the axis of every element. They are the same to the axis of the structure. So meaning now that we can call this as axial structure. Why it is axial structure? Because the axis of every segment, the axis of every component is the same. And if you look at the other type, you look at the other picture, then of course they are also the same. So this x-axis is basically the axis of the structure, okay? And the same for this here. Sorry. So this is the axis of one. So meaning now, this, we call it axial structure. The reason is because every segment, the axis is the same. And if you look at the force, they are also at that axis. The force is in the same axis, parallel, and also on that axis. It is not perpendicular to the axis. That means it is a axial problem. And the element, bar element, the element that is representing this kind of behavior is what we call as bar element. And if you look at the spring, it is also the same. You see here, the spring here, they have the same axis. The spring here, they have the same axis. All right. So meaning that we can regard this as axial problem. Okay, so this is to introduce you to our two types of element that we are going to look at, spring and bar. So we are going to start with spring. And by the way, we are going to focus on a serial kind of structure, meaning we are talking about this type of structure, but not this type of structure. But the process is the same. Okay, anyway, so now let's talk model, the element model for a spring. Okay, so everybody, you have your own, you have downloaded this, which is, I know, so this chapter, whatever chapter is, I think chapter 2, but somehow it is written as chapter 2, but we are talking about bar. Sorry, this is bar. I need to go to spring. Yeah. Hold on, where is my spring? I need to have the spring. Okay, I'm opening the file on the spring. Okay, so this is our spring. I'm going to quickly explain to you what's going on here. You have your own recording, so that means you can always listen to me again later on. So this is spring, okay? And you learn from your high school that if you apply the force to the spring, okay, then there will be extension, right? You will have spring extension. This is your spring extension. The spring stiffness is K, and we have this equation here. This equation relates the force that you apply at the spring. Let's say we call it T, okay? And if you know the spring stiffness K, then we can find the displacement or the extension by using this equation. So if you buy a spring from any place and you do not know the value of K of the spring, very simple, just hold the spring at one end. So that is your spring. Okay, and then you will apply a weight at the bottom of the spring. Let's say a Newton, for example. And then you need to measure what is the elongation of the spring. Okay, the elongation of the spring can be 1 millimeter, 2 millimeter, 3 millimeter, 5 millimeter. Okay, and then you can call it delta. So the value of K, you can get it from here. 10 divided by delta is going to give you the K. And of course, the unit is going to be Newton per meter, Newton per millimeter, or pound per inch, for example. So that's the way you do your K. And anyway, we assume that you know the value of your K. But this is basically the physics of the spring, which means that you know that we actually have this relation, T equal to K multiplied by the elongation. Remember, delta is elongation. Now, what you see here is finite element of the spring. Okay, so this is the spring according to finite element. What you see here is the spring according to your high school, when you learned the spring long time ago. But you know that we have this formula over here. So now, number one, you need to put a note on the spring. So I think by logic, you can say, okay, Cik Wahyu, I want to have the note number at the edge of the spring. So you have number one and number two. So you got two notes. And don't forget that you need to have your Cartesian coordinate. So that's why you see that we have over here our x. So we say that is the direction of x-axis positive direction from node number one to node number two. And we agree before that the spring is going to be a what you call it, a axial type of structure. So meaning that it is going to look like this. It doesn't look like really axial, but it is axial. And then let's say you have the force over there. So meaning if you look at this here, the spring axis, at the same axis, at the same also the direction of the force. That means this is what we call as axial structure. Okay, axial type of structure. So because of that, then the spring element is actually an axial type of element. I write it here. If I could, let me check. Very slow. Okay, so now we have our axis and we have our node. And I think this writing here is familiar to you. As the 2x, you understand the meaning of it. So yeah, axial element. So our spring and our bar is axial element type because the loading is in the same direction of, and in fact, the structure of spring and also bar structure, they are also axial structure. So now I think looking at this here, you use, because you know what node is, you know the meaning of the 1x, F1x, the 2x, F2x. We have two forces and we have two displacement. That means we have 2 degrees of, 2 degrees of freedom. 2 degrees of freedom. When we are talking about our triangle membrane, it is 6 degrees of freedom. But in this case, yeah, we are talking 2 degrees of freedom because you have 2 displacement. Okay, so your element equation is F equal to KD. Okay, F equal to KD, and you know that the D is going to be this, and that is your F. Fine. You know this because that is your element numbering, element terms, element parameters. Okay, so meaning you got 2 forces, you got 2 displacement, and of course it is going to be 2 by 2. And our job here is to find what is actually this K11, K12, K21, K22. And make sure you understand what 11 means, 12 means, 22 means. This is matrix. This is what you learned long time ago. You begin to learn long time ago. Make sure you understand all this. Yeah. K21, for example, is of course it is going to be at row number 2, column number 1, row number 2, column number 1. That means it is K21. Fine. And as usual, this is the name of this matrix: element force matrix, nodal matrix, and element stiffness matrix. Okay, F equal to KD. So now let's derive our element equation. Okay. Is there any question so far from you?
No.
I'm going to skip this. Let's look at what we have over here. Can I go 100? Okay. So what you see on the left, is physics. What you see on the right is finite element. On the left, you have T, the tension force, equal to K delta. Remember, delta is extension. And on the right here, you have what we call as finite element of a spring. So this is spring element, this is the way we draw our spring element. Okay, now let's do physics. Okay, D1, let's do mathematics and physics. D1x, okay, D1x is displacement at node number 1. D2x is displacement at node number 2. Okay, and we assume positive is on the right direction. I hope you agree with me. Okay, that the elongation of this, meaning if you have a spring and you pull it, then the total elongation of the spring is equal to displacement at node number 2 minus displacement at node number 1. That one over there. I hope you disagree with, I hope you agree with me. Sorry, I hope you agree with me. If you disagree, you are wrong. Okay? So the only correct thing here is you believe me, meaning that the elongation is going to be D2x minus D1x because it is correct. If you agree with me, that's fine. If you don't understand why it is so, then it's simply just physics combined with mathematics. Make sure you understand. Make sure you understand. How you understand that? Just look at this carefully, properly, and then try to have some insight on what's going on here, and then you will understand. I don't know how to explain this. You have to sense it, right? Okay. So that's the fact that you need to establish now. I'm going to skip this part. Delta is equal to UL minus UO. I'm going to come back later. But what important now is that you know the elongation is D2x minus D1x. Now, let's do some observation on what you have on the left and what you have on the right. You have two forces, T to the left, T to the right. Over here, you have F1x and F2x. I think you agree with me that this F2x is going to be that T. Of course, right? Just by simple logic. If I apply the force, then that force is going to be the same force that you have here on your finite element model. So F2x is going to be positive T. But F1x, look at the direction, compare to this direction, then F1x must be minus T. Okay, I hope you agree with me. What does it mean? It means that T is going to be minus F1x. The same, right? F1x minus T, T minus F1x, right? And T from physics is K delta. What is K? K is the spring stiffness. K is not the element matrix, no. T is the stiffness of the spring. Okay? So T equal to K delta. K delta is of course K multiplied by this here, because that's our delta. So T is equal to K D2x minus D1x. But of course, that is T. What about F1x? F1x is of course minus T. Okay, F1x is minus T. Because of that, then F1x is going to be K multiplied, instead of this, then just D1x minus D2x. Okay, so that's your F1x. So what about F2x? F2x is going to be equal to T, just like what we have over here. Sorry. So that is F2x equal to T. And of course, T is K delta, and K delta is K multiplied by D2X minus D1X. Okay, so what we have here, I have two equations. The first equation and the second equation. So these two equations can be written in this way as matrix. F1x and F2x is going to be your element forces. D1x, D2x, okay, is going to be your displacement matrix. And then this F and D is connected by the K. And this K here is not the same as that K. This K here is actually your element stiffness matrix. And this K here is actually the value of the spring stiffness. So this is spring stiffness, and this here is the element stiffness matrix. But of course, the value inside is going to be the spring stiffness. So this K minus K minus K is the spring stiffness. So meaning if the K here is 50, for example, then this is going to be positive 50, minus 50, minus 50, and 50. Okay? So what we have here? What we have here is F equal to KD. All right? So what we have here is F equal to KD. Okay? This here. And you know that F is actually this one. D is actually that one, and the value of K11, K12, K21, K22 depends on the value of your spring stiffness. If let's say this is 1000, then of course what you have inside the K is going to be 1000 minus 1000 minus 1000 and 1000, okay, which is based on this equation. All right, so with that, then we finish our element equation. So this is the way we derive our element equation using what we call a stiffness method. Okay, stiffness method. Any question? So based on your understanding on what we have here, I'm going to give you the quiz on spring, I suppose, Monday. And then you are going to label and you are going to know the value of element equation for every element. So I promise you that for your quiz on Monday. Okay, so no question? Are you sure no question?
One question, bro.
Yes, please.
On slide number 4,
Hold on.
yeah,
Is this one?
yeah, that's one.
Okay.
Just to clarify, I just need to make sure lah.
All right.
The prof said that the left side is simple physics spring question, right?
Yes.
So and the right side is the for the FEM method.
Okay. All right.
Okay, so when we have a spring and there's a force applied to both at both ends,
Okay.
so the element, I mean the direction of the force when we do our like free body diagram on the right side have to be on the same direction as the force applied, right?
Okay, carry on with your question. I'm going to explain. Okay, carry on. I want to listen the
So
whole of the question.
yeah, that's my question. I mean, the force, the direction when we do our F1x, there must be the same direction as the force applied, right?
Okay. Okay. I understand your question, not
I mean,
fully, but I hope my answer is okay. All right. So can I answer now for that?
yes, bro.
Okay. So look at what we have here. Okay. So I'm going to do this. Okay. I hope everybody understand what I'm doing. So now what happened here is I have a spring, and then on the right side I put a support, and then I apply a force to the left. I call it T. So the free body diagram is going to look like this. Okay, let's say yeah, so it's going to look like you have T on the right, on the left, and the reaction on the right, R. Everybody should agree with me that R is going to be equal to T. Okay, R equal to T, because if the reaction is not equal to T, that means the spring is going to walk. This is not dynamic of rigid body. If T on the left is not the same as R on the right, that means this is not a structure. This is a moving body. So that means for this to be a structure, that means this spring is not going to go anywhere. The spring will remain to stay there, only will have elongation. So because of that, then R equal to T. If R here is higher than T, if R here is higher than, what am I doing here? Okay, I'm not very good on this. So if let's say R is higher than T, then your spring is going to raise the right. The opposite is if R is less than T, then the spring is going to move to the left. So for this structure to be a structure, that means your reaction here, reaction there, must be equal to the applied force. So now I'm going to, because of that, then I can do this. I just erase everything. Okay, so now what you see here is a physics of what you have learned before. And I think you agree with me that initially, the length of this is L. Okay, and because you apply this force, then of course it will elongate. So now it is having that elongation to the left. I call it delta. I hope you agree with me. Okay, and that delta is based on this equation. Fine. So now you see here that actually that's what I explained to you just now. So actually we can do the same. Whatever now, let's say if I do this, and instead of this, then I apply the force right, for example, then it is going to be the same story. The same story. That means your reaction is going to be to the left. All right. So the same story also, if let's say what you do is this, T, then of course you are going to have reaction to the right. But now instead of elongation, you have compression. Instead of elongation, you have compression. And your equation remains the same. If you do it, then you are going to have the same result, actually. All right. So I hope I answered the question. Is there any additional question that you want to have? Okay, are you happy with that kind of answer? Or there are things that you still not feel comfortable?
Okay, Prof. Thank you, Prof.
All right. Okay, give me another 5 minutes to finish the last slide that we can do today. Are we still on sharing? Yes. So now you understand that the element equation is F equal to KD is actually given in this equation. So meaning that every spring element, that is going to be your equation. So now let's say I have this structure consists of 2 springs. Okay, the structure consists of 2 springs. So it is what you see here is basically your finite element model. What you see here is your finite element model. Fine. So now let's say the modeling is given as what you have here. You have 2 springs, so very straightforward. You are going to have 2 elements of spring. And the node numbering is going to be, it's up to you. So you will have 1 node over here, 1 node over here, and another node over here. Okay, so that would be your node numbering. And then you have 2 spring. Spring number 1, spring number 2, element 1, element 2. Somehow, the way we do node numbering is a bit show off probably. If I were you, then actually, of course, this is me who is doing this. Actually, a simpler way is going to be node number 1, node number 2, node number 3, but somehow it is 1, 3, 2. It's okay, it doesn't matter. So for the element number 1, the spring stiffness is K1. For the element number 2, the spring stiffness is K2. So what you need to do now is you need to write number 1, element equation number 1. Okay, element equation number 1, that one. And then element equation number 2. All right, please observe that for the element number 1, the node is 1 and 3. Okay, so that is element number 1. And that is element number 2. All right. For element number 1, the node is 1 and 3. For element number 2, the node is 3 and 2 as written there. Okay. So now what you need to do is you need to write the equation. So for element number 1, it is going to be, yeah, it's a bit difficult for me to write this down. F1 and F3, okay, in X direction. I find it a bit difficult to write 1 and 3. X over there, okay. And then, of course, over here you have D1X and D3X. D3, sorry, this is really ugly. All right. And then, of course, you need to fill in the inside. Okay, so if you come back to this here, K minus K minus K minus K, that means it is going to be K1 minus K1, and over here minus K1, and also K1. Okay, and then you can do the same for node for element number 2. For element number 2, then it is going to be similar, but over here you will have F3X, F2X, and then D3X, D2X. And then, of course, inside here you will have based on K2, K2 minus K2 minus K2 and K2. Okay? But why you see this 3 by 3 on the left, and also for the element number 2, also 3 by 3? The reason is because you are going to construct F equal to KD. You are going to construct this F capital and D. Okay, and if you look at this here, remember the size of K for this is going to be 1, 2, 3, 3 by 3. The element is 2 by 2. But the structure is 3 by 3. Why it is 3 by 3? Because, of course, it is having 3 nodes. Every node 1 degree of freedom. Only X displacement. Then it is going to be a 3 by 3. And F equal to KD is this one here. This is your F equal to KD of structure. So this is structural equation. What you see at the top is element equation. And it means that as the final structural equation is a 3 by 3, what you need to do is you need to expand. You need to expand the element equation from 2 by 2 like this into a 3 by 3 like what we have over here. So let's see this element number 1. This is F1, F3, D1, D3. So actually, there is no node number 2. Element number 1 doesn't have node number 2. So if I delete this node number 2 from here, then that's what you have. You see here, what you see here is that equation. And the same story. For element number 2, you don't have node number 1. So actually, I can just delete this. Then you remain only with this one. And that is actually your element equation written as 2 by 2. Okay, I think probably it's a bit too tiring for you now. I'm going to repeat this again on Wednesday. So on Wednesday, what we will do in the so-called our lab, I'm going to focus on this. I'm going to try to finish this spring and bar on Wednesday. That's the plan. That's the plan. So that you know how are we going to treat mathematically this analysis, and if we have time, then we can do our lab. But I'm going to focus on Wednesday to this analysis. So hopefully, yeah, we can do that on Wednesday and complete everything. And then on Monday, I'm going to give you a quiz related to what I explained today and also on Wednesday. All right, so I think that's it for today. If you have any question, so what I would like you to do is please listen again to the video of this, and then on Wednesday, hopefully you can have questions to things that you don't understand. It is 10 o'clock already now. Okay, so all right, see you on Wednesday. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good morning to you all, dan selamat berpuasa ya untuk esok hari. Thank you very much.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.